Okay, everyone. I think that we have most of our participants back. So Prasad, I think we can go ahead and start with the lightning talk from our research fellows.
All right. I hope you had a good networking break. Now we'll have our fellows give lightning talks. I'd like to start with the first fellow. Anurag, Anshu will be giving their first lightning talk.
Oh, hi, Prasad. Yeah, let me quickly share the screen. Well, wrong slide. Sorry, one sec. There we go. Yeah. Okay, so this talk will be about learnability of Hamiltonians from quantum many-body Gibbs states. This is a joint work with Srinivasan, Tomataka, and Mehdi, which came last year. So the central object of our discussion in this talk will be quantum many-body systems, which are a collection of particles, let's say a collection of qubits and so on, which interact locally. So a Hamiltonian looks like a sum of terms where mu's are some real numbers, they're between -1 and 1, which reflects the fact that there are no very strong interactions in nature at a local level. And e's are some operators. So for example, e's could be 4-qubit polys, which is shown in this picture. Each placket corresponds to a poly. So that's our setup. It's a Hamiltonian that describes that governs properties of the system. So a Gibbs state is a special quantum state that is derived from a Hamiltonian, which essentially is exponential in h up to a factor which is called inverse temperature. And z is a factor which normalizes the quantum state. The goal here is that given independent samples from the Gibbs state, where the terms mu are unknown, can I figure out what mu is? That is, can I figure out mu prime, which is a vector of m numbers, which approximates mu. So this is the problem of learning the Hamiltonian, because the parameters mu specify the Hamiltonian. There are several motivations why one want to figure out this, solve this problem. So, well, very broadly, learning the Hamiltonian is the first step towards predicting properties of a physical system. So things like spectral gap of a Hamiltonian, the structure of the lattice, and so on, they play a very important role in the physics of the system. And also in statistical machine learning, graphical models are very important objects, which are the classical analogs of this problem, and they're very widely studied. In very complex materials, there's something known as an effective Hamiltonian, which governs the interaction between coarse-grained particles. And they can be very hard to understand unless one really tries to learn them. And in fact, some Hamiltonians even govern the entanglement properties. So learning them is a very natural task to figure out what the entanglement looks like. More recently, in quantum algorithms, Gibbs states play a very important role, and verifying that my quantum system is producing the right Gibbs state is an important task in designing quantum computers. Finally, Gibbs states can also approximate quantum states at low temperature. And if you learn Gibbs states, then we can also learn other quantum states. So our result is an algorithm that solves this problem with a number of samples that's polynomial in the number of particles. And this is also tight up to a factor of 6. So there's a lot of scope for improvement. And the algorithm is pretty simple because it performs some small measurements on the quantum state, followed by classical processing. It's time efficient in some cases, which is the classical processing part. I can quickly tell you about the learning strategy in the next 1 minute. It turns out that in the quantum context, or even in the classical context, the gradient of the quantum partition function is something that can be physically observed. So here's a picture of the quantum partition function. And here is a gradient. And we would like to find the point mu star. But experiments only reveal an approximate gradient. That's the red line over here. So that there's an error in the value of mu that you would like. And the key point is that if the quantum partition function curves fast enough, then mu prime can't be that far away from mu star. And that's our goal. So we show essentially that the quantum partition function has this property that it's very convex everywhere. That means it curves pretty well enough. And that is captured by what is known as the Hessian of the partition function. And we show that it's pretty large. It's not large enough compared to classical results where there's no factor of 1 over m, but that's fine for our applications. Improving this m would also improve our power bounds. And classically, these results are easy to prove because what is known as a Markov condition, which is or conditional independence is very well studied classically. It's very well known, but that totally fails in the quantum world. So that's why proving these results is hard. So that's the main technical result, and up to the future work. So the big open question here is to figure out optimal sample and time complexity for all temperatures for this problem. We know so far commuting Hamiltonians can be learned optimally, and also high temperature states can be learned optimally. And the next question, once we figure out this, probably would be to understand the learnability of other important quantum states, such as tensor networks and quantum circuits. As I alluded earlier, they would be closely related to Gibbs states. And that's about it. Thanks for your attention.
Thank you, Anurag. Any questions for Anurag while Stephen Bates sets up? All right. The next speaker is Stephen Bates.
All right. Hello, I'm going to be talking about Learn Then Test. It's a framework for giving confidence intervals for deep learning models, among other things. I should say this is a joint work with some great collaborators, Anastasios, Emmanuel, Mike, and Li Hua, who are all at Stanford, Berkeley, and involved with the Simons Institute in various ways. Okay, so the setting for kind of this, this talk or this method is the following. So we have a lot of really great predictive models in the modern world to do things like image processing, text processing, and so on. But they're often very complex, right? So if I want to use a state-of-the-art computer vision model, it's going to have hundreds of layers and be very, millions or billions of parameters and be very challenging to understand in a sort of brute force way. When I deploy something like this, I still need to talk about uncertainty or statistical performance, right? I can't just deploy it, use my point predictions, and then pretend I'm getting great results all the time. So what am I going to do in a setting like this? Okay, so that's what we're going to, that's why we introduced this Learn Then Test algorithm or framework. So it has basically 3 steps. You start off with some model F hat. And so this is going to be a deep learning model, say. Okay, you can get it with any architecture, any optimizer, whatever you want. It's some black box that we're then going to kind of probe to extract rigorous confidence intervals, say. Okay, so if I'm doing classification, I want confidence intervals. Step 2 is going to be parameterizing a family of possible confidence intervals. And I'm going to parameterize it by this parameter lambda. You should think of it as a one-dimensional parameter. Okay, so on top of my deep learning model, I have one parameter that goes from small intervals to big intervals. And I'm going to figure out where I need to be to get valid confidence intervals. Okay. Now, what I'm going to do is I'm going to choose that final parameter, that one small parameter on top of the network via multiple testing so that you can get rigorous statistical guarantees about the output. Okay. So let's make this concrete in the case of classification. So I'm going to start here with some model F hat. F hat is, again, something like a ResNet or any deep learning model. And let's say it spits out softmax scores for each class. Like I'll say that there's K classes here, 1 to K. Okay. I can kind of hypothesize a set of reasonable confidence intervals or confidence sets in this case, because the output is discrete, as follows. I'm going to take all the classes Y where the softmax score, this kind of estimated softmax score, exceeds some threshold lambda. Okay. So I'm going to pick the top classes, all the classes that have probability exceeding lambda for some lambda. This is kind of a set of possible confidence sets indexed by this parameter lambda. Okay, and then I'm going to choose that lambda to get 90% coverage. How do I do that? I look at some fresh data. Okay, I kind of make a plot for different values of this lambda. What is the coverage I see on fresh data? So coverage here means what fraction of my confidence intervals or my confidence sets actually contain the true label. Okay, I just plot that. I look at that number and I see where it hits 90%. Or if I wanted 90% coverage, I see where it hits 90%. Now, I'm glossing over some of the details. I don't use exactly 90%. You have to adjust this based on statistical fluctuations. But there's a kind of a small constant here that you increase in order to make this all statistically valid. But morally, what you do is you're just going to use some fresh data to tune the confidence intervals to have 90% observed coverage. Okay, So again, this is the point I see on my little bit of extra data where I got the right coverage, and I'm going to deploy that value of lambda on future data. Okay, so that now is my confidence set function going forward. Okay, so now the magic here is that we have a precise statistical guarantee. With high probability, you'll have at least 90% coverage on future data. And this statement is agnostic to the true distribution of the data or the network you started with and so on. So it's not assuming anything about the distribution or your model and so on. And this delta here, the small probability constant, you get to pick that. I can pick it to be, say, 1%. Okay. I'll refer you to the paper for all the details. But again, this is you're tuning this low dimensional parameter in order to get the correct confidence intervals. I should say that in this particular setting with confidence intervals, there is previous work that we're building on here. What I find most exciting about this is that you can do basically anything now. So I'll show you an example from object detection. In object detection, you have you're given an image like the one on the left, and you have, in this case, 3 goals. You want to identify distinct objects. You want to segment them or find the pixels corresponding to that object. And then you want to classify them, okay? There are kind of error rates associated with these criteria. So I want to kind of have high recall. I want to find most of the objects. I want to have good segmentation. So I want to have high intersection over union with the real masks. And I want to have good coverage. I want to find the right class most of the time. And it turns out with this algorithm, this 3-step algorithm I showed you before, you can do that. Here's a quick simulation experiment where you can see you have good coverage, you have good IOU, and you have good recall because you pick the parameters in this way. Okay. All right, so I'll conclude with that. Okay, my screen stopped updating, but that's okay. I'll wrap up with that. Thanks very much for your attention, and I'd love to take any last questions you have.
Thanks, Stephen. Any questions for Stephen while Siddharth sets up?
I don't see any.
All right.
I can ask a question. Stephen, hey, it's Cindy. So are you assuming like with your fresh data, you have to be able to do some sort of like hold out a validation set or something, right? So we're assuming like supervised? Yeah.
Yeah, it's supervised, exactly. So there has to be ground truth data with, say, the real labels. Yeah.
Okay, awesome, thanks.
Our next speaker is Siddharth Bhandari.
Yeah, hi, thanks Prasad, and thanks everyone for coming to the talk. So I'll be talking about how we can use exact sampling to get better samples. And I think 1 second. Okay, great. So this is really more like a meta statement I want to make about when we have some local procedure to sample approximately. Can we do something to ensure better quality of samples? But let me give you an example to sort of make what I'm saying more concrete. So let's take this famous hardcore model that we all study in statistical physics, which is essentially just a model for sampling independent sets. So you have a graph of some max degree delta, and each vertex can either be occupied configurations where no 2 neighbors are occupied. That is essentially the independent set in this graph. And each independent set is assigned a probability proportional to lambda to the power its size. So lambda here is the fugacity parameter, which controls the kind of distribution we are looking for. If lambda is 1, we are essentially looking at a uniform distribution over independent sets. If lambda is large, then we are preferring the independent sets which are larger in size. And this is used to model the behavior of hard spheres in statistical physics, but it has been a classical playground for studying various sampling algorithms in TCS and statistical physics. So the local changes we make here is the popular Glauber dynamics, which works on the space of all independent sets. And it works in this very simple way, which I guess many of us know. And just very quickly, it chooses a random vertex. So given an independent set I, it chooses a random vertex, and it chooses a random number x. And then depending on whether it can update A, so let's say that it can update the randomly chosen vertex to be occupied, then it does so with probability lambda over 1 plus lambda. If it can't, in cases it chooses the vertex A, there is no way to update the vertex A to be 1 because there's already a neighbor of A which is 1. If it can't, then it just keeps it to be empty. And if it can, then with probability lambda or 1 plus lambda, it updates the vertex to be 1, like in case it chooses B. So it's a very simple random process, which is very local, and we keep on applying it again and again. And hopefully the idea is that after some time, we will get close to the distribution we want, which is the stationary distribution of the chain. So then if we can do that, why are we interested in doing something more than this? So one of the big issues here is that firstly, you need, if you're going to use this procedure in practice, you need some guarantee on the sample quality. And usually this requires proving mixing time bounds, which is not very easy. And even if you succeed using a lot of cleverness to prove a mixing time bound, the given instance that you are running that unless you either you have to rely on heuristics, or the other option is just running it for the time steps larger than the actual mixing time. Use this framework of exact sampling, like besides being elegant and interesting, it also provides you with a stopping time criteria. So it sort of turns the table in a different way. It says that, look, I don't know how long the algorithm will run, but whenever it stops, the quality of the sample is never suspect. So it can sort of get this advantage, that on your use case, the running time might be much lower. And it's not like a heuristic argument saying that, oh, the sample quality, if it meets some statistics, is going to be good. It is sort of like a mathematical guarantee that the sample quality is exactly what you want it to be. So to give you a sample of what actually happens in this kind of arguments. So like if we take the previous global dynamics we study, with very little with very little extra work, we are able to produce a sample which is exactly according to the distribution we want, rather than having to run it for the given number of time steps and proving a mixing time bound. So it basically works by this idea of sandwiching. You use two different chains and you run the global dynamics on those individual chains. So you can see that I have two chains here, top and bottom, and they are not independent. The top chain is not an independent set, but that's okay. And you run the global dynamics update on both the chains using some joint coupling or something, and you will get two different chains, and then you add an extra rule of swapping. So this is the part where we need to design some cleverness into the algorithm. And you swap the updated vertices. So in this case, the vertex B was updated. So you swap the state swap step every time you use the global dynamic step. And when these two chains become equal, that is, the states become the same, then we can give up. We can stop the algorithm. And you can see that with very little extra work, we don't have to worry about the quality of our sampling process. As in final slide, I thought I'll show some graphs which demonstrates the amount of steps we need in terms of the size of the graph until these two chains, the top and bottom chains, coalesce. So for delta equal to 4, and delta equal to 5. So these are random regular graphs of degree 4 and degree 5. The number of steps roughly goes like a linear or close to n log n kind of function. And this is what we expect. And a delta equal to 6, we know that this problem sort of is already hard to see. Sometimes it's possible to take advantage of fast mixing without actually being able to prove it. And thanks, that's all. I'll leave you with this slide.
Thanks, Siddharth. The next speaker is Spencer Frei.
Yes. Okay, can everyone see my screen and hear me?
Yes.
Great. Okay, so this talk is called Proxy Convexity, a unified framework for the analysis of neural network stream by gradient descent. And it's joint work with Chuan Gu, who was my supervisor back at UCLA.
So just to jump right into it, this talk is about neural network optimization. And as I'm sure everyone is familiar with, neural network objectives are non-convex. And there's a number of hardness results that specifically show that there is no, in many settings, there's no hope for finding global minima for these objective functions. But yet what we observe in practice is that gradient descent seems to be pretty good at finding good local minima. Maybe they're not global minima, but they're better than what one might expect naively. And so the difficulty of trying to understand this problem from a non-convex optimization perspective is that most non-convex optimization frameworks exist in this setting where all local minima are global. And so the kind of motivation for this work is to try to design new non-convex optimization kind of definitions or frameworks that allow for characterizations of these types of optimization problems. And so we introduced a number of definitions. I'm going to, in the paper, I'm just going to focus on this one definition, just due to time constraints. And it's this definition of proxy convexity. So we say that a function is GH proxy convex if this type of inequality holds, where the way to think about this inequality is that, standard convexity is that the function lies above its first order Taylor approximation. Proxy convexity relaxes that to say that perhaps the function f doesn't lie above its own first order Taylor approximation, but that there is some proxy function h that does lie above it. And perhaps instead of starting that first order Taylor approximation at f itself, we shift it down to start at some function g. So this is a very general and abstract definition that can accommodate very poorly behaved and non-convex h, f, and g. And the type of result that one gets if you have this proxy convexity property is that gradient descent on the objective f will eventually find points where g is at least as small as the best possible value for h. So this is very general, and in order for this to be meaningful for the original optimization problem for f, of course, h and g need to be related to f in some way. And just to kind of go through a quick example of what that might actually look like in an example of a neural network optimization problem is just considering this single neuron problem where you have just a single nonlinearity sigma and the squared loss. And what we can show is that in this setting, a form of proxy convexity holds, where this proxy function g is like the squared loss with this sigma prime term attached. And the proxy loss h is something like the absolute value loss or the square root of the original objective. And so in this setting, well, what our kind of textbook guarantee for proxy convexity says is that because this proxy convexity holds, we'll eventually find some point where g is at least as small as the best possible value of h. And so what that essentially means is that SGD will find points where that is not the global minimum, but like the square root of the global minimum value up to some constant. And there are a number of hardness results which say that we can't hope to find the global minimum. And so this really captures, like in a concrete way, this setting where global minima is hard, but SGD finds good local minimum. And so something that I think is an interesting future direction, which I haven't really explored, and I'd love to talk with people who are attending about, is kind of reverse engineering this in the sense that, what we say is that if we have this GH proxy convex function, we know that G will always be at least as small as H. And so what if we try to reverse that and saying that we have some objective G that we want to minimize? Can we construct some objective function F such that it is proxy convex with G being the proxy function? If we can do that, then we've found an efficient procedure for minimizing G. All we have to do is gradient descent on F. And so I think this kind of reversing this, this procedure leads to possibly some new and interesting ways to minimize non-convex objectives like G by constructing some surrogate objectives F and then performing gradient descent on F. And so in the paper, we also introduce this other notion of proxy non-convexity in the form of a proxy PL inequality. Don't really have time to get into that, but if you'd like to hear more, please just feel free to come up to me in the Gather Town. And yeah, I think I'm right at about 5 minutes. So thanks for listening.
Thanks, Spencer. Any questions for Spencer while Adil Salim sets up. All right. So the next speaker is Adil Salim. We don't hear you, Adil.
Yeah, we can't hear you, Adil.
And now it's better?
Yes, it's better. There's just a bit of friction, but go ahead. Let's see how it goes.
Okay. Up. All right. So you should see my screen. Okay, so I'm going to talk about decentralized optimization, and in particular about an optimal algorithm for the case, or a special case of decentralized optimization. And this is a joint work with Dimitri Kovalev and Peter Ishtarik. So what do we want to do? So in modern machine learning, we have to deal with large models, and we can often reformulate these problems as large-scale optimization problems. So typically, we have a network of computing agents. At each node of the network is located a computing unit. And the goal of the network of computing agents is to run a machine learning algorithm in a decentralized fashion. So what does it mean mathematically? So we can reformulate we can often reformulate this problem as an optimization problem. So so what we want to do is to minimize the sum of the functions fi, okay, the sum of the functions fi distributively across the nodes. And in this work, we assume that the function fi's are smooth and lambda strongly convex. So what does it mean to solve this problem distributively across the nodes? So first of all, local computations will be allowed. So it means that at each node, so as I said, at each node is located a computing unit. And essentially, this computing unit has access to a local variable xi and the local cost function fi. And the computing unit is allowed to compute the gradient of fi at xi. Moreover, in the network, we are allowed to perform some communication steps, which essentially means that the local variable which is located at node I can be shared with the nodes which are connected to the node I. Okay, so for instance, at node 6 we have x6 and it can be shared with the node 2 and the node 1. Mathematically, communication rounds are represented by multiplying the vector of the local variables, so the vector of the xi's, by a matrix K, which is called the gossip matrix. And a classical example of a gossip matrix must satisfy some properties, but the classical example of a gossip matrix is the Laplacian of the graph of the network. So if you multiply, for instance, the Laplacian of the network by the vector of the local variables xi, what will happen is that the xi will be shared across the edges of the network. So now, what we want to do is to study the complexity of a decentralized algorithm. So this complexity will be in terms of the number of local computations, so computations of the gradient of fi, and number of communication rounds, which means mathematically multiplications by the gossip matrix K, to achieve epsilon accuracy. And this complexity will be given in terms of the problems data, which are essentially the condition number of the functions of the local cost function fi, which is kappa, the ratio between the smoothness constant and the strong convexity parameter, and the condition number of the gossip matrix, which is the ratio between the maximum eigenvalue of the gossip matrix with the minimum positive eigenvalue of the gossip matrix. So this defines kappa and K. And we have some lower bounds for the complexity of a decentralized algorithm in the smooth strongly convex case. We know that we need at least square root of kappa logarithm 1 over epsilon local computations and square root of kappa key log 1 over epsilon communication rounds to achieve epsilon accuracy. And what we did in this work is to propose an optimal algorithm for this problem. So an algorithm matching the lower bounds, and this algorithm is obtained by taking what is called a primary dual algorithm and accelerating it using two techniques. So the first technique is Nester's acceleration, so which is a technique to accelerate optimization algorithms. And the second technique is Chebyshev acceleration, which is a technique to accelerate the resolution of linear systems. So basically, these two techniques can be applied, and this way you obtain the optimal algorithm. So I do not have time to explain the math, but let me just mention some future directions. So of course, we will need to go beyond strong convexity because this work is about strongly convex local cost functions. Also, another important problem in machine learning. So, of course, optimization can formalize several machine learning problems, but we also have the task of sampling that is fundamental in machine learning. So, an interesting direction would be to study decentralized sampling problems. And finally, I said that we obtained an optimal algorithm for the problem, which is true, but in practice, the problems have more structure. So perhaps we can do better by specifying the structure of the problems and the algorithms that we want to study. So, for instance, in federated learnings, there are some special structure in the problems, and perhaps we can do better by including the structure in the problem that we study. Thank you.
Thanks, Adil. Our next speaker is Makrand Sinha. Any questions for Adil while Makrand sets up?
I'll ask a quick question. Adil, is your algorithm related to like belief propagation or something, or is it just like superficially look like a message passing algorithm?
Related to what? You said to?
Like belief propagation, like I don't know, some of these sorts of like loopy like message passing algorithms for graphs?
Yes, so actually, so as I said, yes. So actually, something that is hidden in the presentation is that, you know, this Chebyshev acceleration, it's a way to accelerate the communication in the network.
Okay.
So instead of at each step, instead of communicating a message from the current node to its neighbor, then you do several communication steps so that the message go further in the network.
Oh, right. You get some, you go back a few more steps, I guess. Yeah, cool.
Thanks.
Next speaker is Makrand.
Hi, can you see my slides?
Yes.
Hi, so I'm Makrand, and I'm a SEMS Berkeley postdoctoral fellow, and I will talk about maximal advantage for quantum query algorithms. So the main question here is sort of understanding the power of quantum computing, especially in relation to long-term perspectives, because we know that quantum algorithms can do certain tasks that we don't know how to do classically, like factoring large integers, but there's still a lot that we don't know about what can we do with it in the long term. And one aspect of this question is, designing better quantum algorithms, but the other aspect, which is often much harder, is to rule out all classical algorithms to solve your problems, at least in an efficient way. So here in this talk, I will talk about this question in the model of query complexity, which is a simplified model where you can understand these questions in a rigorous way. So let me introduce this model. So this model, the algorithm gets the input as a black box, and it can access the input by making queries to the input. So for instance, a classical algorithm in this model, it can use random bits to query bits of the input, and the answer is that particular bit of the input. And the goal of the algorithm is to sort of compute some function of the input it is interested in, and to minimize the number of queries simultaneously. So here, we're sort of making a simplifying assumption that the most expensive part of the algorithm is really interacting with the black box and that computation. So sort of that is the number of queries is serving as a proxy for our running time. And all the other operations the algorithm does, they don't cost us much, so we are not counting them. So in this model, you can sort of compute any function with n queries, because you can access the entire input. So the maximum running time in this setting is at most n. So this is what a classical algorithm does, and it also has another name. I mean, this is the same as a decision tree. Query algorithm first queries a bit x1, and depending on that, it chooses another bit to query and so on. So this is exactly what a decision tree does. And so these are completely equivalent. So quantum algorithm is essentially the same as a quantum analog of decision tree, just allowed to make more powerful queries, which are called superposition queries. So now instead of querying for a bit, it can query input bits in a superposition, and the answer is also given back in a superposition. And sort of this is a very, very natural model to understand quantum algorithms, because essentially almost all known quantum algorithms, they fit in this framework, including famous ones like Grover's search or Shor's factoring algorithm. And so far, the rigorous guarantees we have about them, especially when comparing them to classical, most of them are proven in this model of Frei complexity. So now in this talk, I want to ask the question of, what's the maximal separation you can have between the number of quantum and classical queries needed to solve the same task? So what is the task that gives the quantum algorithms the maximal advantage in this model? So this has been studied since the early days of quantum computing from the 90s. And prior to our work, the best separation was constant versus n to the 2/3, meaning that there is a quantum algorithm which can solve the problem with only constant number of queries. But classically, it requires reading n to the 2/3, making n to the 2/3 queries to the input. And what we show in our work with Nikhil Bansal is that sort of a certain problem that is called k-fold correlation gives a constant versus almost linear separation. So essentially, n is the maximum running time in this model. So this is, in some sense, the best separation you can hope for between quantum and classical algorithms. And this was conjectured to be the best possible separation, this problem, k-fold correlation, by Abrahamsen and Ambinis. And in our paper, we show this. And let me also mention that there was an independent work showing essentially the same separation for a related problem. So let me, in the last 30 seconds, just tell you one key idea that sort of went into proving this. And it's about understanding what makes quantum algorithms different from classical algorithms. So I haven't told you what this k-fold correlation problem is, but it's about computing the value of a certain degree k multi-line polynomial. And k is constant for us, so it's a constant degree polynomial in many variables. And one feature this polynomial has is that quantum algorithms can compute it very efficiently with just constant number of queries. But now we want to say that classical algorithms cannot compute this constant degree polynomials, even if they make lots of queries. For this, our main contribution is to show that sparse polynomials, even if they have very high degree, they cannot solve this problem, k-fold correlation. And it's one key distinguishing feature between quantum and classical is that classical models can somehow compute only sparse polynomial in a certain sense. And there's a lot of nice mathematical ideas that went into proving this, including stochastic calculus for analysis. And these sorts of, some of these tools are more common in optimization and approximation algorithms, and they help a lot in solving this problem. So I will leave it at that. Thank you very much.
Thanks, Makrand. Any questions for Makrand while Kevin sets up? All right. Next speaker is Kevin Tian.
Cool. Can people hear me okay?
Yes.
Okay, awesome. Hey everyone, thanks so much for coming and to my lightning talk. And my name is Kevin, and I'm a final year PhD student at Stanford University. Today I'm going to talk about an exciting line of work which focuses on bringing advances in robust statistics to practical fruition using SDP techniques. So this is based on several joint works with my wonderful collaborators pictured here. I want to give a special shout out to Cherry Lee for helping introduce me to this research area, and he's a collaborator on all the works I'll mention. So my research interest is understanding fundamental challenges in modern data science through an algorithmic lens. These challenges are often simultaneously statistical and computational in nature, where we both want to have good estimation or learning rates from limited samples, and also don't want to use too many computational resources such as time or space. To solve these problems, I often have to combine new iterative methods, which are tools for harnessing the data as effectively as possible, with high dimensional statistics insights, which try to understand the geometry of the data. Okay, so concretely, I'll focus on robust statistics today as a microcosm of this blend of techniques. To set the stage in classical ML and statistics, we want to perform some kind of learning task from samples. These tasks are typically information theoretically impossible unless we assume some regularity about the problem, such as learning from independent draws from a suitably nice distribution. In many modern settings, this is maybe too much to hope for. This is where robust statistics comes into play, where we want to design estimators or learners beyond this nice IID setting. So I study robust learning under the strong contamination model, where nature first draws n independent samples from an underlying distribution D, and then an adversary can inspect these samples and replace an arbitrary epsilon fraction of their choice with anything in the support. So we receive the corrupted data, but we still want to estimate something about D. This is a powerful contamination model, which captures problems like data poisoning and training deep neural nets, as well as model misspecification, where the generative model is only close to being a well-behaved distribution. Okay, so for a long time, the only estimators known for robust estimation under strong contamination ran in exponential time in the dimension. So it's a very challenging problem. Recent breakthroughs gave the first polynomial time algorithms, and these often follow the filtering paradigm, which I'll describe here. So we'll use mean estimation as a running example, where under the strong contamination model, we want to estimate the true mean. And the first step of filtering is to answer an identifiability question, which says, okay, maybe I can't, or I don't know how to robustly learn, but can I at least tell you when my data set is tampered with, like something's wrong? For example, it turns out that whenever the empirical mean is a bad estimate for this mean estimation setting, the covariance must be larger than it should be in some direction. So we can actually use this fact as a certificate of corruption, which lets us design scores for filtering. The basic idea is that the certificate proves that the bad points must be responsible for this certificate, like large variance. So we can downweight based on correlation with the top eigenvector while preserving most of the good points. Okay, so we can use this to design a downweighting scheme in polynomial time by making sure the filter removes some point in every iteration. But in high dimensions, maybe polynomial time is still too slow. Right, so can we do better? So taking a slight detour, semi-definite programming, or SDP, is a generalization of linear programming to matrix-based constraints and objectives. So it turns out that since what we're looking for is basically ways to decrease the covariance operator norm, the SDP community has designed tools for exactly this purpose. So a popular SDP solving approach called matrix multiplicative weights rephrases SDP as a game, where we receive some gain matrices GT, and the algorithm plays responses YT with trace 1, which yield this sort of regret bound. By setting these gain matrices G to be empirical covariances, this is actually exactly what we wanted in robust statistics. So maximizing the left-hand side of this regret bound over all trace 1 matrices U exactly corresponds to bounding the empirical covariance operator norm. Okay, so roughly our scores used to be trace products with a tensored top eigenvector of GT. And matrix multiplicative weights suggest that we instead use trace products through this YT instead, which ends up being some kind of smoothed version of a top eigenvector that can capture multiple directions at once. And by using filtering to decrease these inner products with YT and fast numerical linear algebra to compute approximate scores, we're also in great shape to decrease the regret bound's right-hand side. Okay, so some straightforward calculations show that as long as we successfully filter each round, we can repeatedly have the covariance operator norm in roughly log d iterations. So the whole algorithm terminates in polylog rounds of filtering, and this is nearly linear time. Cool. So it turns out that this perspective on using lightweight optimization techniques to speed up learning algorithms based on identifiability proofs is very powerful. And it applies to a bunch of other tasks, including learning mixture models, PCA, and stochastic optimization. For each, we give nearly linear time algorithms with near optimal statistical guarantees by designing custom iterative methods, which can harness the geometry of the problem. So each one of these has its own story, which I can't do justice to on one slide. So I'm happy to go into more details during questions or offline. There's also a lot of exciting work to be done in this area still, so I'm happy to talk about that as well. And thanks so much for your attention. I hope you enjoyed my talk, and here are links to the papers if you're interested.
Thanks, Kevin. Our next speaker is Melanie Weber.
Can everyone see my slides?
Yes, thanks, Melanie.
Great. So I'm going to talk about Riemannian optimization. So I'm going to talk about Riemannian optimization, and the work in this area is motivated by the following observation. So in many applications, we encounter non-Euclidean data. This can be in the form of graphs, strings, or matrices. And in such settings, it can be beneficial to represent the data in on a manifold, so in a non-Euclidean space, as opposed to using a standard vector space setting. And this is particularly interesting if this different geometric lens gives us some nice algorithmic properties. So for instance, related to geodesic convexity. The class of problems that is the subject of this talk is constraint optimization. So here we have a function defined on a Riemannian manifold, and we want to find its minimum subject to constraints. This is a challenging problem with the currently existing tools in Riemannian optimization, because that field has mostly focused on unconstrained optimization. So in my joint work with Zhou, who's at MIT, we looked into designing algorithms that can directly handle constraints. So we can start by getting some intuition about from the Euclidean setting, where this problem has been studied for several decades already. And there are essentially two approaches that people have considered. The first one are projected gradient methods, which are essentially extensions of the gradient descent algorithm to constrained settings. So here we perform a classical gradient descent update, which may carry us out of the feasible region. And then we compute a projection back onto the feasible region to ensure that our update stays feasible. Now, depending on the geometry of our constraints, computing such projections could potentially be expensive. And in such cases, it's better to use a projection-free method. Projection-free methods are guaranteed to stay feasible without any projection step. And we ensure this by first computing a subroutine, which is called the linear oracle. And this subroutine gives us a point in the feasible direction, which just fulfills the constraints. So in our example here, that's a point on the boundary. And then we linearly interpolate between our current iterate and that point, and then step with a certain step size along that line. Now, if we move this idea to the Riemannian setting, we can write down a generalized linear oracle, so a generalized subroutine, which has the same algorithmic idea. And then instead of performing that linear interpolation, we are now constructing a geodesic with the starting point being our current iterate, and then the endpoint being that point zk that is returned from our linear oracle. And this Riemannian equivalent of the Frank-Wolf algorithm recovers similar convergence guarantees to what we have for its Euclidean counterpart. So in particular, if our objective function is geodesically convex, so that's convexity in the Riemannian setting, then we get a global sublinear convergence rate. So as I said, that is exactly the same complexity as what we get for the Euclidean Frank-Wolf algorithm. And that's also comparable to what a Riemannian gradient descent would achieve. So if we encounter in practice a constrained Riemannian optimization task and we have to decide which algorithm to use, it really comes down to investigating how expensive is it to compute a projection and compare that to how expensive it is to solve that subroutine, that linear oracle. So that can be quite challenging in general, because the subroutine is actually non-convex. So one approach that we could take is to numerically estimate, to numerically approximate a solution to that linear oracle, and then we can show if that approximation is reasonably good, then we can retain those global sublinear convergence guarantees. And the more interesting case are special cases and specific Riemannian manifolds where we can actually solve this in closed form. And in such cases, this renders the algorithm into a very practical algorithm. And I want to show one example where this is possible. So if we take the manifold of symmetric positive definite matrices, and we impose interval constraints, then we can solve this in closed form. So one practical example where we encounter this is the Karsha mean problem, which asks us to compute an average over a set of symmetric positive definite matrices. That is a problem that is non-convex through the Euclidean lens, but geodesically convex through the Riemannian lens. So one example where this translation to the Riemannian setting really gives us some benefits. And then I also want to show some brief numerical results for this problem. So here we see the Riemannian Frank-Wolf algorithm that I showed you in blue, and then also two other variants that I didn't get to cover. And if you look through those plots, you see that for different sets of parameters, we significantly outperform state-of-the-art methods due to this nice practical algorithm with the closed form solution of the linear algo. Thank you.
Thank you, Melanie. Our next speaker is Alex Wein. Any questions for Melanie while Alex sets up?
I don't see any.
Hey, can you hear me okay?
Yes.
Okay, I'll go ahead and start then. Let's make sure the slides are working. Okay, so let me jump right in and tell you a bit about the settings. So let's sort of imagine that we want to extract some kind of a hidden signal from a large noisy data set. This is a fairly generic setup that we might imagine we encounter in practice. And so how do we design the best possible algorithms for this type of task? Well, there's a few criteria we're probably interested in. We'd like to have statistical efficiency, meaning that we can find the signal even if it's weak, or maybe equivalently that we need, the least amount of data possible or fewest number of samples possible. And on the other hand, we also care about computational efficiency. We want a fast runtime so that we can scale this to huge problems. But actually, it's sometimes fundamentally impossible to achieve both of these goals simultaneously. And so I'm interested in determining which types of trade-offs are possible. So here's kind of a concrete toy example for this kind of setup. So imagine that the data is a random n-vertex graph. Let's say every edge occurs with probability 1/2. And now the signal part is a clique planted on k vertices. That just means I connect all of those vertices to each other, like the ones shown in red here. And so the goal is that I give you this graph, you need to find the clique. And so, this problem is believed to have this striking phenomenon we call a statistical computational gap. So here we're plotting k, which is the clique size. You can kind of think of it as a signal to noise ratio. So when the clique is extremely small, it's simply statistically impossible to find it. If the clique is quite big, bigger than square root n, then we know an efficient algorithm, a polynomial time algorithm to find it. But then in the middle, there's this very large hard regime, which is more elusive. So here, you can find the clique if you're willing to sort of do a brute force search over all possibilities, but we do not know any polynomial time algorithm. And these types of gaps are actually ubiquitous. All kinds of problems, sparse PCA, community detection, et cetera, many types of problems inspired by practice have these sort of conjectured hard regimes that we would like to understand. Okay, and so, how can we be sure the hard regime is actually hard? Maybe it's fundamentally hard, or maybe we just need to find a more clever algorithm. And so worst case complexity theory, like NP hardness, actually won't really help us here because these are average case problems with random input, right? Just because max clique is NP hard, it doesn't mean I can't solve planted clique on a random input. And so we need a way to prove or argue about computational hardness of statistical problems. And why do we want to do this? Well, a few reasons is because it can tell us when to stop looking for a better algorithm. It can predict which problems are likely to have better algorithms than the ones we currently know. And it can give us even some guidance of what a better algorithm should look like. And so, how actually do we prove or give evidence that problems are hard? Well, one common approach is to show unconditional lower bounds against some restricted class of algorithms. So we propose some large class of algorithms that we believe are maybe sort of optimal, and we rule those out. And so proposals for this class of algorithms, a bunch have been made. So here are a few of them listed. But I want to talk about a different proposal that's more recent called low-degree polynomial algorithms. I won't even try to formally define what this class of algorithms is, although it's a bit what it sounds like, and you can read on the slide here as well. But in the last minute or so, let me try to convince you why I think this low-degree polynomial algorithms are a very sort of promising and exciting avenue for understanding these kinds of problems. So there's two reasons, really. The first is that it is actually tractable to prove failure of all of these algorithms for various problems. And in fact, the proofs are somewhat user-friendly and so can be broadly applied to whatever your favorite problem might be. And we often can prove optimal results, really proving that these algorithms fail all the way up to this conjectured hard phase. And then on the other hand, these lower bounds are sort of meaningful because these low-degree polynomial algorithms actually do capture the best known algorithms for a whole slew of different statistical problems. I won't try to get into the subtleties of exactly what I can consider a statistical problem, but I do sort of believe that they have a better track record than these previous frameworks that I mentioned. And somehow why this happens is because low-degree polynomials do capture a bunch of concrete classes of known powerful algorithms like spectral methods, approximate message passing, things that typically yield the optimal algorithms for things. So if we can rule out low-degree polynomials, we can also rule out a bunch of these concrete approaches. And so now these low-degree lower bounds are actually fairly widespread. Originally, they were introduced for the hypothesis testing problems. So these papers here were really the ones that first came up with this idea of looking at low-degree polynomials. And much of my recent work has been about extending this theory to not just hypothesis testing, but all kinds of different statistical problems. So maybe recovering the signal, optimizing random functions, refutation, and certification. All right, and so I will leave you with a few references if you'd like to know more. Yeah, thanks a lot.
Thank you, Alex. Any questions for Alex while Angela sets up? Our next speaker is Angela Zhou.
Hi, I'll be talking today about stateful offline contextual policy evaluation and learning. This is joint work with Nathan Callis. I'm a postdoc here at FODSI and Simon's next semester. So this project, let me summarize as it's trying to find the class of Markov decision processes or dynamic programs for which our recent progress in causal inference and single time step causal inference can actually solve quite well. So first, let me provide some exposition on single time step causal inference and this research program on heterogeneous treatment effects. So single time step causal inference is the setting on the left. I'm going to assume that I have some data sets of X covariates, A actions or treatments, and outcomes Y only for the treatments that were historically administered in the data set. And so the key problem in causal inference is that of off-policy evaluation or learning. So I have this data set, these treatments were given suboptimally, and I want to assess what is the causal impact of deploying an improved algorithm, and how do I therefore optimize to find the best algorithm for assigning treatments to individuals to maximize my causal outcomes. So the data, of course, reflects this fundamental missingness pattern. Nonetheless, why can't I just take averages in treatment components to estimate the effects of policies? Well, it's because A is actually correlated with outcomes in my data set. So if treatments were assigned by some algorithm, that algorithm was optimized for some target. And so therefore, treatments will be correlated with outcomes in the observational data. So that's single time step causal inference. There's been a lot of progress in heterogeneous treatment effects, where I assume that individual responses to treatment may actually vary in a way that is predictable from covariates. I'm going to talk today about a class of sequential dynamic programs that's quite common in operations research and which is solvable by single time step causal inference. So what is different about this class of dynamic programs? An example is allocating interventions to improve homelessness for different individuals, but also considering additional capacity constraints. So the key different structure is that I'm going to expand the state of a dynamic program, and I'm going to consider a setting that can be thought of as offline contextual bandits. So I have IID arrivals of individuals. They have a causal response, and given their causal response, then I know deterministically what the state transitions are. So this is a very common model actually for many practically deployed algorithms in operations research. You may not be so interested in those specific problems. So what is interesting about this is just understanding how the causal structure of data changes the algorithms or control policies that we might be interested in. So let me talk more about the problem setup. And this is a very insights-driven project in the sense that once I set it up, this becomes more obvious in hindsight because I'm just reading off the causal structure of the data. So a Markov decision process, there's some state from which I take an action, and then I transition to the next state. The key specialization in this is that the transition probability is being given by a causal model from this individual. X denotes covariates for individuals which arrive IID. So this is the kind of offline contextual bandit nature of the problem. Once I observe the response of the individual, I deterministically know how the system transitions. But the kind of key argument here, and I'll illustrate this in an example, is that in this class of problems, suppose that the causal response is conditionally independent of the system state. So I'll illustrate this for the case of airline revenue management or dynamic pricing. So there's a lot of algorithms that have been successfully deployed in this context. And the assumption corresponds to whether or not you purchase an airline ticket at a given price is independent of the number of seats left on the plane, which is the system state known to the decision maker, once you condition on the price that is being given. So that's the kind of key assumption. And if your problem setup satisfies that assumption, then your problem is as hard as single time step causal inference. So what do? We do some modeling. Our key insight is that you can estimate expectations over a single arrival by reusing data from all arrivals. And that is what I'll call single time step causal inference. I won't go into the details about estimation. It's in the paper. But what are our key improvements? I would say our key improvements are if you apply generic dynamic program or offline reinforcement learning ideas, you will incur this dependence on horizon many additional nuisance functions to estimate. On the other hand, by specializing into the problem structure, you recover the kind of right dependence on the number of nuisance estimates, and this can help in practice. So just to summarize our results, we study the sample complexity. You do get some improvements by pooling the data, of course. We have a problem structure dependent sharp characterization of error amplification, which establishes that confounding matters even in these more simplified dynamic programs. And I won't talk about the results, but this helps in practice compared to trying to apply generic RL that is not tailored for this problem structure. So I'll just conclude there and say thanks.
Thanks, Angela. Any questions for Angela?
I don't see any.
Thanks to all the fellows for quite an intense and informative session. The next item on the agenda is we'll hear from our program organizers, but let's take a quick three minute break before that, and we'll resume the session at 12:22, and we'll hear from all our program organizers and all the activities that are going at SEMS this year, and see you at 12:22.